Okay. So yeah, the motivation for this talk is going to be doing inference in spatially extended dynamical systems. So we can kind of think of that as some sort of PD or SPD model. And the particular kind of aspect of that problem that I'm going to be concentrating on is, can we exploit that spatial structure to do inference in a more efficient manner? And in particular, if we are using a particle filter, can we use it to overcome the kind of classic weight degeneracy issue that we would typically expect to see if we naively applied a particle filter to these very high-dimensional models. So to explain this image here, the idea is we have some underlying field defining our state. So here this is just on a two-dimensional spatial domain. And we somehow partially and noisily observe that. We could just run a particle filter in that whole state space, but that would typically very quickly become degenerate, because if we imagine that our kind of state dimension here, if we discretize this onto some mesh, is a function of the number of mesh components, we're in a kind of thousands or millions of dimensions. What we could do is try to exploit the idea that maybe observations don't affect all states in an equal manner. So we had a bit about this, I think, earlier in the week from Jin's talk about spatial localization methods which are applied in ensemble Kalman filters. If we do that in a naive fashion in a particle filtering setting, it's quite easy to end up with introducing a lot of spatial noise into the inferred particles. So if we sample effectively particles at each different spatial point independently, we end up introducing this kind of white spatial noise into the system. There's been work at applying ideas from optimal transport within a particle filtering setting. So there's this work by Sebastian Reich, which he kind of referred to in his talk in the opening workshop, called the ensemble transform particle filter. That also has this kind of nice spatially localized counterpart. And there we're now performing a kind of deterministic transformation between our kind of initial prior particles and our posterior particles adjusting for observations. That kind of leads to these more spatially regular fields if we apply it in practice, but there is still some sort of discontinuities there. And so we're looking at an extension to that idea, which kind of imposes further smoothness on the update to try and end up with something that after the update, after we've assimilated observations, looks much more like the level of smoothness that we observe in the actual underlying true state field. So all of this is joint work with Alex Thierry. So yeah, the problem we're going to be interested in is performing inference in some spatially extended dynamical system, and usually that will be defined by some partial differential equation model, often with some stochastic element. The kind of typical applications we might imagine for this are things from the geosciences, like numerical weather prediction or ocean modeling. The key challenges in that specific sort of domain are going to be that, as I said, the state space, the effective state space, is going to be very high dimensional because we're typically looking at some spatial discretization of a continuous field. Often these models are very expensive to simulate, so we're going to have this kind of computationally limited ensemble size. We're not going to be able to use lots of independent instances of this model just because we don't have the computational budget for it. And typically, we're going to be working in a regime of models where the kind of filtering distribution will be non-Gaussian due to the inclusion of nonlinear dynamics within the model. So just to set out the notation, I'll generally refer to the underlying system state, which is what we want to infer, as x, the observations as y. And then also there will be these two additional random variables, which this m of t, which defines the noise introduced in the state updates at each time step, and then this n of t, which is the observation noise, so the noise which is used to generate the observations at each time step. I'll use a shorthand for the dimensionality of the state and observation spaces. And if you see this kind of subscripted by a range notation, so some terms subscripted by 1 to n, I just mean this kind of index set of terms, and similarly for a superscript. And I'll use that quite a lot just to keep things succinct on the board. So the model we're assuming here is that the dynamics are Markovian, and that we can basically specify it by some set of state operators, update operators, that'll denote f. So the idea is we simulate some initial condition just by taking some noise variable and then mapping it through some function. This could be some initial kind of Benin simulation of your PD, say. And then thereafter, we update the state by applying a state updater to the previous state and potentially including some noise. So often this might be additive noise, but we're not restricted to that case. So the observation, similarly, we're going to assume some sort of conditional independent structure in the terms of they're only depending on the current state, so that y of t is just a function of the current state x and some additional noise variables. So again, to define a little bit more notation for later on in the talk, we'll just assume that the distribution on the observations has some well-defined density given the states, so this G. And then the kind of main object of interest throughout this talk is what is going to be the filtering distribution. So I'm only ever going to kind of consider the online case here where we're just inferring a current state given the observations up to that state. So we might also want to do smoothing, but we'll concentrate on the filtering case. So I'll denote that by this pi of t. And then also useful for kind of expressing the algorithm that we're going to be talking about is this predictive distribution, which is just the probability on the next state given all of the observations up to the current time index. So succinctly, what is a filtering problem? Well, it's the task of trying to infer each of those filtering distributions given a set of observations. And generally, as I said, we will try and do this in an online manner. So the kind of basic idea underlying all of the methods that I'll talk about here is this idea of a kind of recursive update to our approximation to the distribution. So given a filtering distribution at the current time index, we can kind of map that forward to a prediction distribution via what I'll call this prediction update. And then given that predictive distribution, we then perform some assimilation update to take into account the observation to get to the next filtering distribution. The prediction update has this form here. So what we're saying here is that we push forward through this state update operator averaging over the noise variables. And then the assimilation update, which will typically be the kind of harder to account for in practice, we can kind of think of it as just Bayes' rule. We're taking into account the current observation density, and we're having to renormalize. The class of algorithms that I will consider as what I've kind of denoted ensemble filters here. So that's algorithms in which we're representing the filtering distribution at each time index by a system of particles, such that we can kind of make this empirical distribution approximation to the filtering distribution. And then we can kind of very simply implement a prediction update to get predictive distribution particles just by simulating from the system effectively. So drawing some noise variables for each particle and then mapping forward through the state update operator. So this is just basically saying propagate our forward our states under the system dynamics. So the first algorithm I'm going to talk about is this ensemble Kalman filter. So this is a kind of Monte Carlo or ensemble variant of the Kalman filter, introduced originally by Evanson and with some later corrections by Burgess et al. So the Kalman filter is the kind of an efficient implementation of the exact inference steps we perform for a linear Gaussian model. Even if we have a linear Gaussian model in the sort of dimensionalities we're talking about, doing the exact Kalman filter update would typically be intractable just because of the dimensionality of the matrix and vector object we'd be working with there. So in general, the Kalman filter cost would scale quadratically in the state dimension, and linear in the observation dimension in computation, and in memory quadratically in the state dimension. And if the state dimension is, say, of the order 10 to 6, 10 to the 7, this is kind of going to be problematic in practice. Whereas if we use a particle representation of the distribution, we can reduce this to something which scales only linearly with the state dimension. So the key thing about the ensemble Kalman filter in terms of this talk is that although it's an efficient filtering method, which has been used a lot in the sort of applications I discussed at the start, so kind of things like numerical error prediction, it is only consistent when we have an underlying linear Gaussian model. So if we think that nonlinear effects have a strong effect upon our filtering distribution, such that it's not well approximated by Gaussian, this is going to be kind of somewhat fundamentally limited in how well it can approximate that filtering distribution. So the basic form of the ensemble Kalman filter update takes the following form. So we're going to specifically talk about here what's sometimes called the stochastic ensemble Kalman filter. And this has a very kind of simple intuitive form. So we first simulate observations given our current state ensemble. So we just map them through this observation operator plus simulate some observation noise variables. And then the form of the assimilation update just takes this form here. So it's just some additive term involving the difference between the simulated observations and the true observations modulated by this Kalman gain matrix. So I haven't given the specific form of this here. It involves kind of solving some least square system within the simulated ensemble, state ensemble, and observation ensemble. But we can kind of think of it as a Monte Carlo estimate of the true Kalman gain that we'd use in the Kalman filter. So yeah, this is the more simple variant to describe. In practice, we can kind of get rid of this initial simulation of observation noise using these square root ensemble Kalman filter formulations, and that's what we would typically use in practice. So as I said, the issue with the ensemble Kalman filters, or one of the issues, is that they kind of make this underlying linear Gaussian assumption, and we, in some cases, like to get away from that. So a natural choice of class of algorithms which are able to deal with more general models is particle filters. So these are consistent for the sort of models we're interested in as the ensemble size goes to infinity. So the basic idea is we're going to kind of recursively apply an importance sampling type algorithm. So we define importance weights just in terms of the observation densities evaluated at the current particle values, and then normalizing these. And this then gives a kind of, given the predictive ensemble, a importance-weighted empirical approximation to the filtering distribution at the next time step. So in practice, once we recurse this algorithm, we do resampling to try to re-equalize the particle weight. So we basically try to create more copies of the particles with high weights and eliminate particles with low weights. We can kind of parameterize this resampling as this idea of drawing a series of binary 0, 1 random variables that will denote R here, which satisfy some certain conditions. So there only to be, for each particular, say, column of this matrix, we want there to only be one variable equal to 1 with the rest 0. And then we want an expectation that the proportion that are, so if we sum over the rows, that the proportion in each row is kind of defined by the particle weights as calculated with the update formula on the previous slide. So these two conditions together will mean that this overall update is consistent in the large n limit. There are different ways we can implement this actual resampling. We kind of trivially can do something like multinomial resampling, where we resample each of these sets of R variables independently from some multinomial distribution, the indices corresponding to that multinomial distribution. Or we can do things like systematic resampling, which are lower variance in practice by using fewer uniform random variates in the generation of random variables meeting these conditions. So I'm now going to introduce the ensemble transport filter that I mentioned briefly at the start of the talk. So the idea here is to propose an alternative to that resampling step that we just discussed. So resampling takes an empirical distribution approximation to the predictive distribution and then maps that to an equally weighted empirical distribution approximation to our filtering distribution, our posterior effectively. We could also, rather than doing that stochastically, consider using ideas from optimal transport to come up with some map which transforms between those two empirical distributions. And Sebastian Reich, in this 2013 paper, proposed exactly that idea. So if we define a kind of discrete optimal transport problem as follows, so that we want to find, this is some, what we'll call the transport map or transport matrix. So this is of dimension p, the number of particles, times p, the number of particles, with entries bounded between 0 and 1. So we want to choose this such that it minimizes if we consider this as defining some joint probability distribution on the indexes before and after the transformation, we want to minimize the expected distance between the particles before and after the update. We need to do that, though. This optimization is constrained by the requirement that we define a transport matrix which has the correct marginal distribution, such that once we map through this matrix, we end up transforming to a distribution with uniform weights, given we originally have these non-uniform weights. So this is can be expressed as a linear program and efficiently solved using things like the network simplex algorithm. So that will generally scale cubically in the ensemble size, solving that sort of system. But given this defines a valid way of updating a set of an empirical distribution from a weighted form into one with equal weights. So if we wanted to kind of correspond exactly to the particle filtering case, what we would do is actually look at the joint distribution defined by this transport map and then resample according to that. In the ensemble transport method, Sebastian Reich instead proposed using this linear transformation directly via the transport map. So this will not be equivalent to resampling according to that distribution for some finite number of particles. But these transport maps have the property that as p tends to infinity, they become increasingly sparse and have only 0, 1 entries. So some underlying kind of deterministic map, effectively, between the two empirical distributions as the ensemble size grows. And so, although this will be, in some sense, the incorrect update to do for some finite n, we still maintain consistency, just having through this fact. So as p goes to infinity, we'll still would end up getting the correct answer. And the nice thing about just defining this linear transformation is that this overall update is now deterministic. So in a simple setting where we're just working with, say, some low-dimensional problem and implementing a particle filter, this is not really going to buy as much. So this is just a different way of effectively implementing the resampling update, which is quite computationally costly because it involves these cubic cost optimal transport solves. But we'll see later when we're talking about the ability to spatially localize particle filtering algorithms, the deterministic form is fairly key to getting that to work well in practice. So far I've kind of discussed things in a very general setting without relating back to the kind of initial motivation of models defined on spatial domain. So I'll just define a bit of notation now to kind of move into that specific setting. So I'll consider the spatial domain to be in general compact and just this set S, and that it'll have some distance metric on it, which might be the Euclidean distance, but for example, if we're looking at things with, say, a toroidal topology, it might be the kind of corresponding distance on the torus. We make this relatively weak assumption that the observations are independently observed at L spatial locations. So basically that we can attach some sort of spatial location to each observation, and that given the current state, all of those observations are independent. So although the underlying spatial domain will probably be some continuous object, in practice we will typically discretize it to some mesh or grid. So then our kind of effective dimensionality of X will be a multiple of the number of components in that mesh. So this will typically be a high dimensionality but finite, rather than considering strictly the kind of infinite dimensional case where our state space is a function space. So as I kind of alluded to at the start of the talk, typically we would expect particle filtering in high dimensional settings to perform quite poorly. So in particular, if the observation dimensionality is high, the particle weights will tend to become degenerate. And so that just is kind of intuitively what that's saying is that with high probability, only one of the particles will end up with significant weight after renormalizing, so that if we then do resampling or some other form of update to respect those weights, we'll basically map from p particles down to one particle. So we lose all diversity in an ensemble. So even in a kind of a simple Gaussian case, you can show that the required ensemble size to avoid this degeneracy issue will scale exponentially in the model dimension. So if we kind of think of the sort of dimensionality we're considering here, we can see this is clearly going to be intractable. So this kind of suggests that there might be little hope of using particle filters within the kind of spatial models we're interested in. And it has, in fact, limited the direct application of this kind of very simple particle filtering algorithm that I have described so far within spatial models. So, because not only are we not able to state afford an exponential dependence on our, say, observation dimensionality, in fact, actually, our ensemble size will typically be orders of magnitude smaller than even the observation dimensionality itself. So, say in your numerical weather prediction system, in an ensemble setting, typically, say, P might be of the order of 100 at most. So that's just the limit of, given the expense of running that model, the number of independent instances we might be able to simulate. What is the observation dimensionality, as I said, could be of the order of 10 to the 6, 10 to the 7. So this seems kind of that it might be kind of non-starter, as in if we know even in simple Gaussian models we have this kind of exponential dependence, how we're ever going to work with these more complex systems. So in general, that is going to be a difficult problem, but if we can enforce some more structure on the underlying model, we can possibly make some progress. And so this key idea, which the methods we'll talk about in the rest of the talk, exploit is what's sometimes called this decay of correlations property. So this is the idea that in a spatial model, if it's defined on some large spatial domain, typically we'll expect that the state variables will be only dependent or only strongly dependent on observations which are located in some sense close by in space. So we don't expect, say, the local weather in a particular part of the world to be influenced by observations, say satellite observations, at the opposite side of the world. So this is, as I said, called this decay of correlations property. So it's a kind of heuristic property. It's quite hard to exactly formulate what we mean by this and to measure it in practice, but it is something that we typically expect to see in the kind of large-scale geophysical models that we are interested in simulating. So this property is actually key to how ensemble Kalman filter methods are applied to these large-scale geophysical models in practice. So there is these localized variants of ensemble Kalman filters, which are what are typically used in these very large models. And how those localized methods work, or at least at a very kind of top-level description, is that we define some, what I'll call here, a localization kernel. And this is just some function which takes as input the distance between a pair of points, some value between 0 and infinity, and outputs a weight between 0 and 1. And that should kind of monotonically decrease with the distance. We assume generally that it outputs a value of 1 at 0, and then outside of some finite distance r, all values for r, small r bigger than big R, for this localization radius r, this kernel is equal to 0. And so what this does in practice is we use it to modulate the strength of the dependence of each of the update to each state variable given a particular observation at a different location. So if we have a state variable at position S and an observation at position SL, we modulate the kind of the update to that particle value at that position by a term which is proportional to this kernel. So the details of how that's applied in the ensemble Kalman filter, there are different ways of doing it. We can use this to taper a covariance matrix, which the kind of observation covariance matrix, or we can also do things in a kind of a pair observation setting where we just look at some limited spatial domain around each observation. But it seems natural, if this is a kind of key component of making the ensemble Kalman filter work in high-dimensional models, whether it's possible to apply it within a particle filtering setting. And this is an idea that has had quite a lot of interest over the last decade or so, and there's been various attempts to implement this. It's not a trivial thing to do, but there's been some initial theoretical and empirical results which suggested that it could be a promising way forward. So the idea behind this is if we only use a small subset of the observations to calculate kind of local particle weights, so that we, instead of having just a single weight for each particle, we in some way make these spatially extended, and then at each position calculate weights which depend only on the observations close by in some sense. By reducing the kind of effective local observation dimensionality, we are hoping to kind of move into this regime where we're, again, not getting degenerate weights. So a very simple instantiation of this idea was described in this paper by Rabashini et al. It was what's termed the block particle filter. So here we take our spatial domain, and then we basically partition it into a set of disjoint blocks. And then for each of those blocks, we just consider them as being completely independent to each other and run the particle filtering algorithm I just described on each block independently. And then within each particle filtering algorithm, assimilating only the observations that are local to that block. So if we put some assumptions on the forms of the state updates within a model, so in particular these local mixing assumptions, which are quite equivalent to or analogous to the typical assumptions that are often made in practice in the time dimension to look at the asymptotics of particle filtering in terms of stability over time. So this is the kind of spatial equivalent of those sort of models of boundness on our transition densities. This, very naive block particle filter is still able to give an approximation error bound, which is independent of the model dimension. So a key issue of this method, and why I've been describing it as naive in some sense, is unsurprisingly, because we're treating each individual block of our space independently, we're going to end up with this these biases at the block boundaries, because we're not accounting for dependencies between variables across those boundaries. And in some ways, this is going to introduce discontinuities in the states across space. And in some systems, this could be quite a kind of pathological effect. So if we have some sort of PDE system that we're simulating using a finite difference method, introducing sharp discontinuities like this could have a very negative effect on the kind of gradient calculations within that finite difference method. And just more generally, obviously, this is kind of a somewhat implausible state if we assume that the kind of underlying state dynamics produce state fields which are smooth like those on the left. So I alluded to a little earlier about this idea of computing local particle weights. So just to make clear, a very basic scheme for doing that. So in this figure here at the top, we just have an ensemble of free particles, which are these 3 different spatial fields. And we assume we have kind of sparse observations of the underlying true state that we're wishing to refer. So that's on some grid, we just have a set of observations. And again, making the assumption that the log likelihood decomposes as a kind of sum of terms at each of those observation locations. We can define the log likelihood term for each observation and evaluate it at each of these different free particles. And that will give us, again, some sparse grid in space for each of these observations corresponding log likelihood terms. Now we take this localization kernel that we defined before. So this is just some compactly supported kernel on our spatial domain. And effectively, we convolve that with this these sparse log likelihood fields to produce smooth localized log weight fields. So if we took that kernel to just be the whole spatial domain, effectively we would map to we would sum across all of those weights and we would get a single particle weight or a constant weight across the whole field equivalently. And that would just be the standard particle filtering setting. As we reduce the kernel, we define weights which only locally depend on a smaller and smaller subset of the observations. So once we move into this localized setting, we move away from anything that we really know, at least at the moment, how to kind of come up with strong asymptotic guarantees for. But the hope is that we might buy something in terms of reducing weight degeneracy, basically. So when I discuss localized weights, basically I'm talking about something like this, and I will kind of refer to these objects later in the kind of algorithm that I'm discussing. So if we've defined a set of local weight fields, we then might consider how would we actually update the kind of predictive distribution particles to reflect those calculated weights. And so this is one of the key issues in defining a localized particle filter method, because it's not immediately clear how to do this in a kind of a way which preserves the properties we want about the underlying particles. So the kind of simplest idea that we could have, perhaps, is just to look at each individual spatial location. So we're assuming here, basically, that, as I said before, that S is in some sense finite. It's a grid of points, and so we could look at each individual S and then just directly apply that resampling update that we had for the single particle case. So for each spatial location, we resample according to the weights calculated at that spatial location independently. And so our overall update will just map at each point in space. We take the predictive particle values at that point in space, resample them according to some resampling scheme which respects the correct weights, and that will give us the filtering particle as the output, or a set of filtering particles as the output. So, unsurprisingly, this very simple idea will not necessarily work very well in practice. So again, kind of looking at this kind of toy motivating example, if we have some underlying true smooth state field, this is the sort of inferred field particles that we would get after applying that sort of independent resampling. So we can introduce this kind of white spatial noise via this idea of just resampling independently at every different spatial location. So there are very simple things we could try and do to make that better. So within this ensemble common particle filter paper of Robert and Kunsch, they suggest one way which can remove quite a lot of that noise, which is to, rather than using independent random draws for every spatial location, to use effectively a common random draw across all spatial locations, and to use a systematic resampling scheme such that we only need one random uniform to define the overall resampling. If you implement that in practice, you get fields which look somewhat more like this. So kind of locally, they are smooth. But there are these kind of discontinuities which correspond to sharp changes in the underlying particle weights, where the kind of indexes sampled end up differing. So this is definitely better than this in some sense, in terms of being a bit more similar or more plausible under the kind of model that we're interested in. But still, obviously, we have these discontinuities. And as I said, these can, in practice, be quite a pathology if we're working with these PDE models. So another way we could consider updating the particles gets back to this ensemble transform method that I discussed earlier. And so this is what we're actually going to form the basis of the algorithm I'll go on to talk about. So in this follow-up to Sebastian's original paper with one of his postdocs, I think, they kind of proposed this localized variant of the algorithm, where rather than computing one transport map rather than computing a single transport map for the whole system, they compute individual transport maps for each spatial location. So kind of equivalent to that kind of naive resampling scheme I just talked about, but doing that using via transport maps as opposed to resampling. So as I said when discussing the ensemble transport method, the update defined by that transport map is deterministic. And so if we apply that across space, we don't introduce spatial noise. However, what you're doing under the hood there is solving some linear program to calculate the optimal transport map. And that is not a smooth function of the inputs to that linear program. And so although we do get much more regular looking fields out of it, we still don't get the kind of a preservation of the underlying smoothness of the field. So the kind of fields we get out are definitely significantly more regular than those by using resampling-based methods, but they're still not as smooth as perhaps we'd want in practice. There's also a kind of computational issue here that now we're going to have to solve an optimal transport problem for every single grid point. For the kind of ensemble sizes we're looking at, of say p equals to 100, these optimal transport problems are relatively cheap to compute. So they scale cubically in p, but something of order 100, that's like a 100 by 100 matrix multiply. It's pretty cheap to compute on a computer, but if we're doing that for, say, a mesh of 1 million or 100 million points, that can become somewhat of a bottleneck. Although that should be kind of, the proviso to that is if the actual model dynamics that we're simulating are relatively complex, even that relatively high cost of simulating all of those, so sort of computing all of those optimal transport matrices will typically still be orders of magnitude smaller than the actual model integration cost. So this can, for simple models, become a computational constraint that we don't want compute optimal transport maps for every grid point. But it's not really a major issue if we're kind of working in the domain of a small ensemble size and a very large model where the dominant cost is the integration of the actual dynamics. Okay, so the idea that's going to kind of underlie the method I'll describe is to kind of extend this idea of the blocked particle filter to smoother partitions of space. So we'll consider what's called a partition of unity on the space. So this is a set of basis functions which at each point in space sum to unity. Typically, we'll assume these basis functions are compactly supported and smooth. And so we can now consider this as, rather than having these disjoint blocks as defining our partitioning, we have this kind of smooth partitioning of our space via this these set of basis functions. And so we can we'll describe an algorithm which uses these within a particle filtering setting in the following slides. Okay, so this is an example of what a partition of unity might look like on, let's say, a two-dimensional space. So we just have a set of these kind of bump functions tiled across our space. How do we use that in practice? Well, if we take our original particles, using that partition, we can basically, by multiplying each of those basis functions by our particles, we can come up with a set of kind of patches of those underlying state fields, which are modulated by this kind of smooth compact function. So now, rather than just having in dimension number of particles, we have something which has dimension number of particles plus the number of basis functions. We can also use those basis functions to map from our localized log weights to probabilities per basis function. So we just integrate against those basis functions to map down from these log weight fields defined across the spatial domain to a set of particle probabilities per basis. I discussed in the kind of ensemble transport setting this idea of we were minimizing some cost which depended on the distance between particles. We could look at the pairwise distance fields between each set of particles, and again, we can integrate that against these basis functions to come up with cost matrices for each basis function. So here we've got a free particle system, say, 16 different basis functions, so we have 16 free by free cost matrices defining the cost of transporting, say, each of those patches. So we now have a set of probabilities and cost matrices which together define a set of optimal transport problems. We can solve each of those independently. So we basically solve for an optimal transport map which will take an empirical distribution with the following weights or probabilities and map to a uniform one, trying to minimize an expectation this cost. So here we will be solving for 16 optimal transport problems. And then we, again, looking at those patches are defined in the kind of first of the series of figures. So they are the basis functions multiplied pointwise with our original kind of predictive distribution particles. We can now do the optimal transform update. So sorry, the ensemble transform update to each of those patches individually. So we're just taking each of those transport matrices and then performing a linear transformation or linear combination of the prior particles via that transport map to get a set of posterior particle patches. And then we merge those particles, so sum across the patches at each different spatial location to end up with our predictive ensemble. So the key thing about this method is by defining all of the operations via this smooth partition of unity, that if we start off with smooth particles and we use this optimal transport-based transformation, which will define a deterministic update, which doesn't introduce noise, then the resulting fields that we get out will necessarily be smooth. There is a kind of tweak factor here that we somehow need to decide how we're going to define this partition of unity. And that's going to be key to getting this algorithm to work well in practice. Fundamentally, our kind of intuition at least is that what you want is that the set of basis functions reflect the underlying smoothness in the field that you want to maintain. So you want to kind of have those basis functions to be kind of defined over a spatial scale, which kind of represents the lowest level of smoothness that you'd like to maintain in the computed posterior particles. That's obviously a very loose definition, and we don't really have a good way of setting the form or number of these basis functions in practice at the moment, other than kind of looking at the results for different choices. So that's definitely something that would need to be worked on to make this a more kind of generally useful method. But to kind of get back to that toy example, whereas before directly applying the ensemble transport method to each grid point individually, we would end up with, as I said, this a lot more regular, but still not kind of smooth field. Using this partition of unity type formulation, we end up with these much smoother posterior particles. And actually, in this case, because we've reduced from, say, having to compute optimal transport problems on this, I think here, 128 by 128 grid, to one that's 8 by 8 for the number of basis functions, we've, in that case, reduced the number of optimal transport problems, and so the overhead cost from that by a factor of 64 as well. So I'm just going to give, I'm short on time, but I will just show a couple of videos to show that we have tried this in some slightly larger models. And I'll just, for the example system, this is going to be this incompressible Navier-Stokes model defined on the torus using a 64 by 64 spatial grid discretization. So our state space here is a dimension 4096. And our observation space, we subsample every second location in both spatial dimensions, so we get 1024 observations. This is relatively toy on the scale of the kind of large geoscience models that we were talking about at the start, but this is still beyond the kind of dimensionalities we'd be able to run a kind of naive particle filtering algorithm without getting weight degeneracy. So I'll compare this, a local variant of the ensemble common filter to this smooth local ensemble transport filter using here an 8 by 8 grid of basis functions. Okay, so this first video is the ENKF. So on the left, we have the kind of true underlying state field we're wanting to infer. So that's some vector field defining the velocities. We observe the kind of curl of that field, so the vorticity field with some noise. And this is a reconstruction from the ENKF. So we can see that it does manage to capture some of the kind of coarse scale resolution of the dynamics, but at various points lose track of them. And that's in some sense coming partly at least from the underlying nonlinearity of these updates and the kind of Gaussian energy assumption made by the ENKF not working well in this case. And if we now look at the ensemble transport polynomial filter setting, so the observations here are quite informative, so it's not surprising we're able to recover quite a good estimate of the field here, and we're not showing anything about uncertainty information here. But here, at least in this particular example, it does seem to be able to recover the underlying true state fields more faithfully than the ENKF, and you can kind of quantitatively measure this using things like RMSC, and we do get quite significantly better performance with the local ATBF in this case. So just to conclude, what we've discussed here is a localized ensemble transport particle filtering scheme, which has this kind of key benefit of maintaining spatial smoothness in the computed particles. We've only really looked at this from a kind of empirical standpoint so far, and so we can't really say anything theoretically about whether or not this partition of unity type formulation is a sensible thing to do, and whether or not there are ways to guide the choice of that partition of unity. And I think that's a kind of key issue that would need to kind of overcome to make this a more generally useful method, just how you would define that kind of basis expansion over your space. So yeah, that's the end of my talk.
function for function of unity. You determine it beforehand, or you can online.
So in the current kind of implementation, it's done fixed beforehand. So we, as I said, the very vague heuristic we have is for if you had some prior simulations of your model, you would look at the sort of spatial scale of that, and then fit, the scale of your basis functions such that they reflect the underlying smoothness. We've got no real reason to assume that's optimal, but in the cases we looked at least gave us some kind of target. But yes, whether or not you could come up with a better heuristic for setting that, or even do it in a kind of adaptive manner, yeah, that would definitely be a kind of interesting direction to look at. And there is definitely, there's a lot of flexibility in that basis kind of expansion. And in fact, you can kind of think of existing algorithms within that. So things like the blocked particle filter correspond to a kind of non-smooth partition where you're using compactly supported blocks across your space. And whether or not you can we could maybe look at some of the theory in that blocked particle filter paper to maybe inform the choice in terms of approximation error and so on. We're not really sure at the moment, but yeah, definitely it's an interesting question to kind of consider.
So I was thinking, do you know the relationship between what you're doing and what people do in computational fluid dynamics?
In terms of,
so it does remind the way you're using these basis functions kind of reminds me a lot of about the stuff that they do there, where they actually want to simulate a fluid, and obviously they want the solution to be smooth as well.
Yeah. So. So the partition of unity is generally used in kind of PD settings often as a kind of concept for defining the underlying, given some finite support, some smooth expansion of that. We're not really sure, I guess. It was mainly a kind of heuristic motivation that we wanted to look at smooth equivalents to this kind of hard partitioning within the blocked particle filter. It would definitely be nice to do this in a more model-based fashion so that we're kind of looking at if we're simulating some underlying smooth field, if we expand that smooth field using a set of basis functions, can we use that within an inference setting as well, rather than this kind of post hoc saying that we have some separate spatial discretization within our model, and then we imply, again, once we're doing inference, some other kind of discretization or way of partitioning our space. So definitely, it doesn't seem this is a very kind of elegant way of doing it. I guess, like you say, if we looked at ways that these PDs are solved in practice and whether or not there is some way of using that basis function expansion more exploiting it in a better way, rather than, as we said, at the moment it's completely heuristic. We just we set it based on observations of kind of simulations from the model. So there's not a lot of kind of strong rationale behind that choice.
So for the EMKF itself, it's based on Gaussian assumption.
Yeah.
So how about your method?
So the ensemble transport particle filter doesn't rely on a Gaussian assumption. As I said, it is consistent in the non-localized setting for the large ensemble limit. You can actually, if you wanted to be more faithful to a particle filter, resample according to the transport map. Because it's for a large ensemble, mainly 0-1 entries, the difference between resampling according to that map and applying it as a linear transformation or linear combination is relatively small. There will be a few pairs of particles where you say average over a couple of particles as opposed to just directly mapping from one particle to the other. But it is, at least in the non-localized setting, applicable to the kind of non-Gaussian distributions. But yes, the resampling versus of just applying it as a linear transformation does, in some sense, introduce some extra approximation bias, but you would still eventually lose that if you made your ensemble size large enough. But how that then feeds into this localized setting, I would say, is very difficult. So the main motivation for using it there is actually just to help enforce this smoothness, rather than, resampling would perhaps be a more natural thing to do in terms of the analogy to particle filtering. It's just, as we saw, it's quite difficult to do that in a way which maintains spatial kind of regularity.